In this video we have three integrals, and they all involve the function ln of x. Can you tell from inspection here which method you would use? Okay, let's look at these. Two of them will be done by a standard u-substitution. The first one though, I'm going to try integration by parts. So you pick your u and your dv. The u you want to differentiate, and the dv you want to integrate. The ln function is very easy to differentiate. So let u equal to ln of x, then du would equal to the derivative of ln of x would be just 1 over x and dx. The dv will be something you differentiate. The only thing we have here is x. We didn't have the x, we might use a 1 for the second part there. So let's let dv equal to x dx. Then integrate both sides. On the left with respect to v, we get v. On the right with respect to x, we get x squared over 2. Over here then, we'll continue. In the formula for integration by parts, it's the integral whatever you pick for u, then it's dv, then it's the product of u and whatever you got for v after you integrate, and then it's minus the integral of v du. Everything works out nicely. This will be pretty straightforward. In some cases, this part here might require a little bit more work. But in this case, we got u and the v right there. I'll put the v in front. I think it goes better. Vx squared over 2. And then the v, or the u rather, will come up next, ln of x. And then it's minus the integral of v, which is x squared over 2. And then du, and du over here is 1 over x dx. So that's multiplied there. We can simplify this. X here cancels with x squared, leaving me 1 factor of x here. So basically this comes down to integrating x over 2 dx. The first part is already fixed. That's going to stay x squared over 2 ln of x. Like I said, for this one here, we're left with x over 2. The x here cancels, so we've got x over 2 dx. Integrate that, we add 1 to the exponent and divide. And this will give us a minus x squared over 4 plus the constant of integration. So that's your answer for number 1 here. X squared over 2 multiplied by ln of x minus x squared over 4 plus the constant of integration. Now for number 2, I'm going to let u equal to ln of x. Normal substitution, u-substitution, du would equal to the derivative of ln of x would be 1 over x dx. So ln of x, that's your u. And the dx over x right here, same thing there, is du. So this is simple integration with respect to u. Add 1 to the exponent here of 1, we get a u squared. Divide by that value plus the constant of integration. Okay, that's the integration with respect to u. Now we just go back to the original variable. So the u ln of x, quantity squared over 2 plus the constant of integration. The next one looks similar. They'll have the ln of x, of course. ln of x here is in the bottom here. But I'm still going to let u equal to ln of x. So there it is. Du, again, will be the same. 1 over x dx. So I'm using the same substitution here. Forget about this part here. So this is going to equal to dx here. Dx over x. Same thing over here. Dx over x. That's your du. and ln of x is u. So anytime you see this set up here, that's the formula. The integral of du over u is always going to be natural log of whatever u is. Natural log of the absolute value of whatever u is. So put absolute values here. Sometimes you won't need the absolute values if the expression you put here is definitely positive, not negative. In our case, the u is ln of x. So the answer to this one is the natural log of the absolute value of natural log of x plus the constant of integration. So again, 2 and 3 were done by standard u-substitution, and 1 was done by integration by parts. And I do believe that's the way to go in these 3 problems. Thanks for watching. We'll see you next time.